When you picture the danger of building an early skyscraper, you picture the height. Men on bare steel, hundreds of feet above Manhattan, one wrong step from the end. On the Singer Building in 1907, 41 stories rising to become the tallest building on Earth, that danger was real. But the crews who worked those open edges managed them far better than most people assume. The deadliest threat on the Singer Building was not the height at all. It was a snapped hoist cable, the very machine trusted to carry every load up the tower. And the reason it failed tells you more about how skyscrapers actually went up than any photograph of men on a beam ever could. The Singer Building did not rise from the streets of Manhattan as just another office block. From the start, it was a deliberate act of corporate self-assertion. Singer Manufacturing Company, already a global force in sewing machines, set out to make its headquarters a physical symbol of its reach and ambition. The company's directors did not simply want a place to house clerks and ledgers. They wanted a monument, one that would dominate the skyline and announce their presence to the world below. To realize this vision, Singer acquired the prominent corner of Broadway and Liberty Street in the heart of the city's financial district. The building was conceived not as a practical solution to office needs, but as a declaration of technological and economic power. Ernest Flagg, the architect, was tasked with designing a tower that would eclipse all others, blending ornate beaux-arts detailing with the latest engineering advances. The final result would soar over 600 feet, briefly holding the title of world's tallest building and casting a literal shadow over the city's older masonry giants. Every element of the project was calculated to impress, from the caisson foundation sunk deep into Manhattan bedrock to the illuminated beacon at the summit. The Singer Building's silhouette became a new icon for New York, appearing on postcards and in newspaper illustrations as a symbol of modernity and corporate confidence. For Singer, the tower was more than a headquarters. It was a public statement, a vertical billboard of industrial dominance. This ambition set the stage for every risk that followed, shaping the pressures and priorities that would define the construction process and, ultimately, its hidden dangers. In 1908, the Singer Building rose above Manhattan, claiming the title of the world's tallest structure for a brief but significant moment. Its tower reached 612 feet to the roof and 670 feet to the tip of its flagpole, surpassing every rival on the skyline. What set the Singer apart was its tower-on-base design, a slender shaft perched atop a massive podium. This form, now a staple of city skylines, was a radical departure from the squat, blocky towers of the previous era. Engineers faced new challenges as they anchored the steel skeleton deep into Manhattan's bedrock, using caisson foundations to support a vertical load that would have overwhelmed older masonry techniques. The building's construction demanded the most advanced lifting equipment of its day, hoisting tons of iron and stone higher than ever before. Elevators, still a rarity in most office buildings, became essential, climbing alongside the steel as it rose. At night, an illuminated beacon atop the tower signaled Singer's presence to ships entering New York Harbor, a deliberate display of ambition and modernity. Newspapers called it a sky-piercing marvel, and postcards showed its silhouette towering over the city's older giants. The Singer Building's brief reign as the tallest structure made every engineering decision, and every risk, part of a new chapter in skyscraper ambition. New York at the turn of the 20th century was a city obsessed with vertical power. Skyscrapers were more than just office space. They were public proof that a company or even a whole city could outpace its rivals by building higher and faster. The Singer Building's ascent from design to completion between the late 1890s and 1908 unfolded in the middle of a fierce race for the sky. Each floor added was a new claim on modernity. Each ton of steel lifted a symbol of progress. The pressure to finish quickly was intense, not just from the Singer Company's boardroom, but from a culture that measured success in stories and feet. Newspapers tracked every milestone, and rival firms watched closely, ready to outdo the next record. In this environment, every delay or mishap threatened more than just the schedule. It risked the reputation of everyone involved. The city's skyline, once defined by church spires and domes, became a battleground of steel and ambition. For the men on site, the drive for height meant working at a pace and scale that tested the limits of both machinery and human endurance. The Singer Building story is inseparable from the urban mindset that demanded ever greater speed, ever greater spectacle, and accepted risk as the price of progress. Popular images of early skyscraper construction often show men balanced on narrow beams, seemingly one slip away from disaster. But while the open edge of a tower hundreds of feet above the street posed a real hazard, the daily routines on the Singer Building were anything but reckless. Crews worked under the steady direction of foremen who enforced a strict system of discipline. Each gang had a clear chain of command, and every task, from riveting to moving materials, followed an established order. To reduce the risk of falls, workers installed temporary steel rails along open platforms and walkways. These barriers, though simple, kept men and equipment from sliding off the edge. Woven netting hung beneath certain work zones, designed to catch falling tools and, in rare cases, a worker who lost his footing. Safety measures like these were not perfect, but they reflected a growing understanding that organization and planning could save lives. The men themselves were skilled tradesmen, often union members, who relied on teamwork and routine to keep each other safe. Four-man riveting gangs, for example, moved in practiced rhythm, each step coordinated by the foreman's signals. The site was busy, but it was not chaos. While accidents did happen, the idea that workers were constantly in danger of tumbling into the void is more myth than reality. Most crews spent their days focused on their tasks, surrounded by rails, netting, and the watchful eyes of their supervisors. The open edge was a source of anxiety, but it was managed with a seriousness that belies the legends. The greatest threats often came from elsewhere, from the machinery and systems designed to lift the building ever higher. Raising the Singer Building from the heart of Manhattan required more than daring men and steel beams. It depended on a machine that rarely appeared in the headlines but made every floor possible: the construction hoist. At a time when the city's tallest towers were still measured against church spires, the hoist was the unsung engine of vertical ambition. Without it, the project would have stalled at the lower stories, unable to move the tons of iron and stone needed for each new level. Every day, the hoist's steel cable lifted workers, girders, and masonry hundreds of feet above the street. The machinery did not just save time, it made the entire skyscraper feasible. Crews relied on its steady rhythm, trusting it to carry both their tools and their lives skyward. The hoist's drum, powered by a steam engine, wound and unwound the cable as loads rose and fell. For the Singer Building, speed was everything. The construction schedule demanded that materials reach the upper floors as quickly as the steel skeleton could rise. Each trip of the hoist shortened the race to the top, turning a months-long climb into a matter of minutes. Iron workers, masons, and foremen all depended on the hoist's reliability. Delays or breakdowns meant idle hands and mounting costs, but a smooth-running hoist kept the project on pace and the company's ambitions within reach. Yet this dependence came at a price. The higher the tower rose, the more critical the hoist became, and the more catastrophic any failure would be. Unlike the open edges, which could be managed with rails and nets, the hoist's risks were hidden inside its cable and gears. A single weak link could turn the machine from a lifeline into a lethal threat. In the rush to build higher and faster, the Singer Building's greatest danger was not always visible from the street. It was the machinery that made the skyline possible, and the unseen forces that could bring it all crashing down. The hoist cable and drum formed the backbone of the Singer Building's ascent, each playing a precise role in lifting the city's newest landmark skyward. The cable, a steel wire rope about 1.5 inches thick, bore the weight of every load sent aloft. Steel beams, bricks, sacks of cement, day after day. Its strength came from dozens of wires twisted into strands, then spiraled together, a design meant to spread the burden and guard against sudden failure. Yet every lift, every pause, every jolt sent microscopic stresses rippling through the steel. Over weeks and months, these stresses accumulated, wearing even the finest wire until a hidden flaw could become a point of rupture. Beside the cable, the drum worked in constant rhythm. Mounted at the base of the construction site, it was a broad steel cylinder, often more than 3 feet across, powered by a steam engine. Its job was to wind and unwind the cable, raising and lowering tons of material with each revolution. The drum's surface was grooved, guiding the cable into neat coils, while a series of pulleys and sheaves kept tension even and movement steady. The speed of the drum determined the pace of the build. Too quick, and the cable risked whipping or tangling. Too slow, and progress ground to a halt. Each turn of the drum bent the cable around a tight curve, a source of fatigue that engineers understood well. Larger drums eased this stress, but space and cost forced compromises. On the Singer Building, the drum's size was chosen to balance power, speed, and the limits of the site. Every day, the cable bent and flexed, invisible cracks forming deep within the wires, out of sight and out of mind. A hand-operated brake could lock the drum, holding a load suspended in midair. But if the cable gave way, the brake was powerless. The entire system depended on the cable's hidden strength and the drum's steady motion. When either failed, gravity took over, and the consequences could be catastrophic. The cable and drum, often overlooked, were the silent guardians of progress and peril alike. Steam power drove the heart of the Singer Building's ascent. A boiler-fed engine delivered force to the hoist drum, its steady beat lifting tons of steel, stone, and tools hundreds of feet into the air. Each movement began with a surge of pressure, a piston driving gears, gears turning the drum, and the drum winding the thick steel cable with every revolution. This was not delicate work. The hoist was built to tackle massive loads, to repeat the same grueling task hour after hour, day after day. Yet for all its strength, the system was not invincible. The brake, a simple but vital lever and wedge device, stood as the final barrier between a controlled lift and disaster. When the operator needed to hold a load steady, he engaged the brake, clamping the drum in place. The entire sequence depended on perfect timing. The steam engine had to deliver just enough power, the drum had to spin at the right speed, the cable had to bear the load without stretching or fraying, and the brake had to stop everything instantly when called upon. If any piece failed to do its part, the consequences rippled through the system in a heartbeat. The hoist was designed for heavy labor, but not for endless punishment. Every lift and every stop imposed stress on the cable and the drum. Metal fatigue crept in with each cycle, wearing down even the toughest steel. The brake shoes wore thin, the drum's grooves deepened, and the cable's inner wires began to fray long before the damage could be seen from the outside. The safety of the entire operation depended on invisible factors, on the integrity of steel hidden beneath layers of grease and grime, on the precision of a brake lever pulled at just the right moment. No single part could guarantee safety alone. The hoist was a chain of dependencies, each link as strong or as fragile as its neighbors. When the system ran smoothly, tons of material seemed to float up the tower with effortless power, but every successful lift masked a delicate balance. The machinery that made modern skyscrapers possible was always one small failure away from turning force into catastrophe. On a workday in June 1907, the routine at the Singer Building site was suddenly broken by a violent snap. The main hoist cable, a steel rope that had lifted hundreds of loads without incident, gave way without warning. In that instant, the machinery that had driven the tower skyward turned into the source of its greatest danger. The cable's failure happened in full view of the men on site. A heavy load, suspended above the ground, dropped uncontrolled. The noise, a sharp metallic crack, cut through the usual clatter of rivets and engines. Workers scrambled for cover as the falling weight crashed through scaffolding, scattering debris across the lift zone. The hoist platform, once a symbol of progress, became the center of chaos. Work halted immediately. The site, usually alive with movement, fell silent except for shouts and the echo of the impact. Foremen rushed to account for their crews while others inspected the tangled remains of cable and steel. The area around the hoist was cordoned off, and the injured were carried out for medical attention. For the first time, the risk that had been hidden inside the machinery, inside the cable's twisted wires, became visible to everyone on the ground. The danger was no longer abstract or distant. It was a mechanical event, sudden and absolute, that left no room for doubt about where the real threat lay. The interruption lasted long enough for city inspectors and company officials to arrive. Every hoist operation stopped while the cause was investigated. In the aftermath, the focus shifted from the open edges of the tower to the lift zone itself. The snapped cable forced a reckoning with the unseen forces at work on every skyscraper site. Where height had once seemed the obvious hazard, the machinery that made height possible now stood revealed as the deadliest thing on the Singer building. A hoist cable under tension is a hidden spring, storing force in every strand of steel. When that cable snaps, the force doesn't disappear. It erupts. The load, once held steady, is suddenly unchained. Instead of dropping straight down like a stone, it often whips outward, driven by the energy trapped in the cable's stretched wires. The result is not a simple fall, but a violent, unpredictable swing. A steel beam or a loaded platform can become a battering ram, smashing through anything in its path, scaffolding, platforms, even the building's own frame. The moment the cable breaks, the load accelerates not just downward, but sometimes sideways, tracing an arc as gravity and leftover tension fight for control. Workers nearby have only seconds, sometimes less, to react. The danger isn't limited to those directly beneath the hoist. Anyone within the swing radius is at risk, as the mass can sweep through multiple levels or ricochet off beams and planking. Debris flies. Rigging nearby can be torn loose, triggering a chain reaction as pulleys, hooks, and even other cables are yanked from their anchors. Secondary damage is common. A snapped cable can whip back toward the drum, lashing out with lethal force. Platforms below may collapse under the sudden impact, endangering crews who thought they were out of harm's way. The chaos spreads quickly. One failure can bring down a web of supports, scattering tools, materials, and men. In the aftermath, the site is left in shambles, the machinery silent, except for the rattle of settling debris. The physics of a snapped hoist cable turn a single point of failure into a rolling disaster, one that exposes the true peril lurking behind the smooth operation of early skyscraper lifts. This is the danger that height alone could never match, the sudden cascading force unleashed when the machinery at the heart of construction gives way. For the men working on the Singer building, the hoist cable was part of the daily rhythm. Most mornings began with the same routines: tools checked, loads prepared, signals exchanged between ground and platform. On the day the cable snapped, that routine was shattered in an instant. The injury reports that survive are sparse, recording only that a worker was struck and another was hurt when the load fell. No names appear in the official logs or in the city's press clippings. The absence of names does not erase the reality. These were real people, not just figures in an accident summary. Each man on the crew had his own reasons for being there. Some recent immigrants, others with families waiting at home, all drawn by the promise of steady pay on Manhattan's tallest project. The danger from a hoist failure was not limited to those riding the platform. Anyone standing beneath the lift zone or even nearby could be caught in the arc of falling debris. A snapped cable did not discriminate. It could lash out unpredictably, striking workers who were simply passing through, carrying supplies, or waiting for their turn on the hoist. The accident turned a place of work into a scene of chaos and fear as men scrambled to avoid the swinging load and collapsing planks. For many, the shock lay in how quickly things changed. One moment, the site was humming with the usual noise of construction. The next, a single failure had scattered injuries across the lift zone, halting the job and sending men to the hospital. The records may be incomplete, but the cost was personal. Behind every brief mention in a report was a disrupted life. A hand crushed, a leg broken, a family left to worry. The story of the Singer Building's hoist accident is not just about machinery or physics. It is about the ordinary workers whose routines could become deadly with no warning and whose experiences often slip through the cracks of official memory. Wire rope, for all its strength, is never immune to fatigue. Each time the hoist lifted a load on the Singer Building, the cable's steel strands flexed around the drum, stretched under tension, and then relaxed. Over hundreds of cycles, these microscopic strains accumulated, gradually weakening the rope from within. Even when a cable looked sound on the surface, invisible cracks could be forming deep inside, setting the stage for sudden failure. The relentless pace of construction only made matters worse. Schedules were tight, heavy materials had to reach the upper floors as quickly as possible. It was not unusual for crews to push the hoist to its rated limits, or sometimes just beyond, bundling extra steel or stone onto the platform to avoid delays. Every overloaded lift increased the strain, hastening the cable's decline. The hoist's brake, meant to hold a load steady, was itself a point of vulnerability. Brake shoes wore down with use. If the brake was not properly maintained, it might slip or fail to engage completely, leaving the cable to bear the full force of gravity on its own. In the chaos of a busy site, small maintenance lapses could go unnoticed until it was too late. Inspections did occur, but the culture of safety in 1907 was still developing. Visual checks were the norm, and the tools for detecting hidden wear simply did not exist. Inspectors looked for frayed wires or rust, but internal fatigue went unseen. Without routine replacement schedules or non-destructive testing, cables were often kept in service until a visible defect appeared, or until disaster struck. No single flaw doomed the Singer hoist. It was the slow alignment of ordinary weaknesses, a cable worn by daily labor, a brake past its prime, the constant pressure to move faster, and an inspection system not yet robust enough to catch every threat. The result was a system that worked until the day it didn't. Modern construction sites approached the dangers of vertical building with a rigor that would have been unrecognizable to the crews on the Singer Building. Today, every steel cable used in a hoist is subject to strict inspection schedules. Rather than relying on a worker's eye or a foreman's intuition, engineers use non-destructive testing to probe for hidden weaknesses inside the wire rope. Cables are retired on a set timetable, not simply when a fray appears at the surface. Redundant braking systems now stand guard against the risk of a single point of failure. If the main brake slips or a cable gives way, a secondary mechanism engages automatically, holding the load in place. This design answers the problem that haunted early skyscraper sites. A single snapped cable no longer guarantees disaster. Load limits are no longer guessed or set by habit. Every hoist is rated with a built-in safety factor, often 4 times the maximum intended load. Engineers calculate the stresses, check the ratings, and document every lift. Overloading, once a shortcut to save time, is now a clear violation of both law and safety codes. Routine has also changed. Daily checks of cables, drums, and brakes are required before any shift begins. These inspections are written into the workday, not left to chance or memory. Regulators conduct surprise visits, and safety officers track every repair and replacement. The result is a system where trust is built on records, redundancy, and verification, not on luck or experience alone. The lessons of accidents like the Singer Building's Hoist failure are embedded in every modern site, turning hard-won knowledge into everyday practice. From the start of the skyscraper era, the dangers of working far above the street have captured the public imagination. Photographs of men perched on beams and stories of fatal falls filled newspapers and safety campaigns. Yet the historical record tells a more complicated story. In the early 1900s, construction sites for towers like the Singer Building were among the most dangerous workplaces in America. Fatality rates for iron and steel workers hovered around 220 deaths per 100,000 employees, nearly double the average for all industries at the time. While falls from height were certainly a hazard, a less visible threat claimed nearly as many lives: failures of hoists, cables, and rigging. Reports from projects across New York and Chicago reveal a steady pattern. Hoist cable snaps, drum failures, and collapsing rigging caused dozens of deaths and injuries each year. At the Metropolitan Life Tower and the Woolworth Building, similar incidents were logged, sometimes with even deadlier results than at Singer. These accidents rarely made the front page, partly because the violence was mechanical and often hidden from public view. A worker struck by a recoiling cable or a falling load might be listed as just another casualty, his story lost in the daily churn of progress. Public memory has always favored the spectacle of a man on a beam, but the numbers show that the machinery moving materials skyward posed an equal, if not greater, risk. The labor records and accident tallies of the era make clear that the real killer was often the hoist, a device both essential and deadly when its limits were pushed or its flaws went unseen. The Singer Building's cable failure was not a freak event. It was part of a wider pattern that shaped the hard lessons of early high-rise construction, lessons that would eventually drive the demand for better inspection, stronger regulations, and safer machines. After the early skyscraper disasters, engineers and city officials began to rethink how hoists should be designed, inspected, and maintained. In the years following 1907, the pattern of cable failures and near misses across New York and Chicago made it clear that relying on luck or a sharp-eyed foreman was not enough. Trade journals and engineering societies started publishing detailed guidelines for rope inspection, urging contractors to check for hidden fatigue inside the steel wires, not just fraying at the surface. By the 19-teens, regular inspection intervals became common practice on major sites, and city building codes began to require written records of every check and replacement. Designers also took a harder look at the hoists themselves. Cable manufacturers increased the minimum diameter of wire rope, aiming to spread the stress over more steel and slow down the onset of fatigue. Drum sizes grew larger, reducing the sharp bends that could crack wires from within. Engineers called for dual brake systems, one mechanical, one friction, to ensure that a single worn-out shoe or missed lever pull wouldn't mean disaster. These changes were not just technical upgrades, they reflected a shift in thinking, from reacting to tragedy to preventing it before a load ever left the ground. Trade associations like the American Society of Mechanical Engineers published new standards for hoist design and operation. Building codes in cities like New York began to define what counted as an acceptable risk, setting out safety factors for every lift and requiring extra brakes on platforms that carried men. The focus moved away from patching things up after an accident toward a system where the weakest link had to be found and fixed in advance. These reforms, shaped by the hard lessons of the Singer Building and its peers, laid the groundwork for the safety culture that would eventually become standard on high-rise construction sites. Most construction deaths today still involve equipment failures, not falls. Each new high-rise relies on hoist systems, now regulated and rigorously tested, but never immune to error. The hidden hazards that once haunted the Singer Building persist in every modern skyline. Safety evolves, but the lesson endures. The greatest risks are often the ones nobody sees coming. Thanks for watching. Share your thoughts on unseen dangers in the comments below.